So thank you for very much for this opportunity to share our work. And also my internet connection is not very stable, so if we experience some troubles, maybe I will have to turn off my camera. So this is the outline of the talk. First, I would like to briefly introduce our group and our approach, which is known as composite-boson or Qubosonic formalism. Then I would like to mention in a few words our research lines. And after that, we are going to speak about our last work, in which we focus on strongly bound fermion pairs on a ring. And we will finish with a summary and some comments. So when finishing the talk, I would like you to have a mental picture on how do we work and what topics do we work on, and why do we choose to work on these topics and with this particular approach. So I am in a kind of new group at the National University of Córdoba in Argentina. My postdoc advisor here is Ana Magtei. She comes from the quantum information area. And we collaborate with Alex Bubri from Spain, who comes more from the atomic and molecular physics area and field body physics like me. We also collaborate with Cecilia Cormick, who has a lot of experience in ultra-cold atoms. And the work I'm going to speak about is our last work with Ceci. So we come from different research areas, but we share the theoretical approach, which we complement with simulations, with numerical simulations. And as I said before, we work with something called the composite-boson or Qubosonic ansatz. This ansatz was introduced in 2001 by Anthony Leggett for bosons and Monique Bascott for fermions. Here are some references. And the ansatz propose an expression for the ground state of a system with certain properties that we will see in short. And the basic idea of this ansatz is to treat a composite particle such as an atom or nuclear molecule as if they were ideal bosons. The simple case could be to think in two bosonic or fermionic particles, making a new composite entity that behaves like an elemental boson. This strategy to deal with composite particles is a widely used strategy in many body physics, and it is justified a posteriori because it works in the sense that it allows us to predict and manipulate the behavior of physical systems. When we think in fermionic particles, the underlying idea is that if we exchange two fermionic particles, the total wave function must be antisymmetric under this exchange. But if we exchange two fermions, the total wave function must be symmetric, like in the case of bosons. Then we can think in two fermionic particles like a new bosonic entity. Of course, when we use the formalism with fermions, we must take into account the Paulie exclusion principle. We interpret that one of the main goals of Monique Bascott, the creator of the Qubosonic ansatz for fermions, is to show that even in the presence of strong fermionic correlations, the Qubosonic ansatz captures the physics of the system. In this context, one of our main goals as a group is to test the ansatz, and that's why we are always looking for concrete applications in experimentally achievable system to contrast the results obtained using the ansatz with actual or real measurements. And one example of such systems are the ultra-cold Fermi gases. And also, as I said before, our group members come from different areas, and one of those areas is the quantum information, and that's why we are very interested in the role of entanglement on the ideal bosonic behavior of composite particles. So we can then we can formulate like two questions or two main questions that guide our work. First, a very fundamental question, which is under which conditions a pair of fermions can be treated as an elementary bosons. Some authors have explored this question and point out that the key to understand the origin of composite behavior relies on entanglement. And the second question is related to the extent of the ansatz in particular and the formalism in general. And this is when can we use it and when we can't. And the results I will show in the next slides are more related to this second question. But before going to those results, I would like to briefly review the Qubosonic approach as formulated by this author, Law. The main idea of the Qubosonic ansatz is then to build the unpolarized state of an even number of particles of two different species upon the single pair state ground state, which is therefore a two-body or two-particle state. For us, these two particles must be distinguishable, meaning that we have two different kinds of particles, A and B, or red and blue. And that could be, for instance, electron of different spins or atoms in different hyperfine states. But the whole system must be unpolarized. We must have the same amount of red particles and blue particles. So in the description proposed by Law, the pairing structure is explicitly used, and the observables are obtained in terms of the a single particle state, and that, in my opinion, makes the results more intuitive or imaginable. Giving a kind of Qubosonic recipe, first we need to find a good two-particle or single pair state, and with good I mean to look for a state in which the interparticle interactions are taken into account in the best way as possible. And after that, we need to find a decomposition of the state reflecting the pairing structure between the two types of particles in terms of the single particle state. This is the Schmidt decomposition of the state. So if we have red particle in a given single particle state labeled with J, then we have a blue particle in the J state, but of the blue particle. Then, based on that decomposition of the single pair state, we define the boson creation operator here that creates a pair of these two different particles like a new entity, having into account that when we create the particles and we fill up the single particle state, we must obey the Paulie exclusion principle. The state of n of such pairs come from successive pair creations from the vacuum. This B here is the vacuum, and requires a normalization constant. This normalization constant has the information about the exchange correlations between particles of the same species among the different pairs of cobosons. That will be this red one with this other red one, between, for example, this blue one with this other blue one here. So this sum here is performed over different states in order to fulfill the Paulie exclusion principle. And it turns out that when the ratio between this normalization constant here goes to 1, the coboson behave like ideal independent non-interacting bosons, while a ratio near or close to 0 reveals strong deviation of the ideal bosonic behavior, meaning that the fermionic character of the constituents of the red and blue particles is important. So when using the Qubosonic ansatz, the many particle physics arises from the state of a single pair and from the fermionic exchange correlations. This means that the interparticle interactions beyond the exchange interactions are only being considered in that initial two-body model for the first pair, for a single pair. And that's why it is so important for us to have a very good model for the first single pair. As I said before, there is a connection between entanglement and the ideal bosonic behavior. And in a few words, Leo point out that the composite particles can be treated as bosons when the red and blue particles are sufficiently entangled. And this is equivalent to two things. First, the effective number of available single particle states must be large compared to the total number of composite particles. And second, the available physical space for each pair must be large than the pair of each one, than the size of each one of the pairs. In other words, we need to have enough single particle state to accommodate all the particles, and we also need to have enough physical space to host all the pairs. And we can think on this like an egg-saver. The cobosons would be the, the eggs, and the states will be the places in the egg-saver. So if we have at most 12 eggs, then we can accommodate them all and we will be okay. But if we had more than 12 eggs, we will have a problems. Also, everything will work with chicken eggs, but if we have a big crocodile egg, this is not going to work. So what this entanglement-related hypothesis says is that if the red and blue particles are sufficiently entangled, then we have a good egg saver for the egg type and also the number of eggs we are dealing with. So we can accommodate or put our cobosons in the state space and also in the actual physical space. As a personal comment, this understanding or addressing composition from many areas or many point of view is what I like the most about the formalism and what keeps me always motivated. I also said that in order to test the ansatz, we are always looking for concrete applications on experimentally observed system depicting strong fermionic correlations, and also systems that were widely studied with other theoretical approach, like exact diagonalization of the Hamiltonian or quantum field theory or quantum Monte Carlo simulations, among others. For example, in 3 dimensions, we study ultra-cold Fermi gases, and in 1 dimension, we study Wigner molecules, the fermionization of distinguishable fermions, and also fermions in a ring. Okay, now we almost reached our last work with the SESI. So the Qubosonic ansatz is expected to work or to be valid for short-range interactions, for dilute systems, and also highly entangled constituents. But it turns out that in this work here, part of our group studied strongly bound composite bosons in a discrete lattice and show that the ansatz fails in this one-dimensional model. And the ansatz fails because it is not able to capture the long-range correlations in the system. In a two-dimensional lattice, the ansatz works, and Anna and Ceci check that the fidelity between the Qubosonic ground state and the true or the correct ground state increases when the two-dimensional system becomes more and more dilute. Then one of the main conclusions of this work is that the dimensionality plays a crucial role. But we still wonder what happens with a continuous system. And that leads us to focus on the case of two fermion pairs on a ring of length L, where the red and blue particles interact with a delta attractive potential. The correct or true ground state for this system is well known. It is solvable by means of the Bethe ansatz, and the ground state for the unpolarized case can be found in this paper, this reference here. So we wanted to compare this known energy with the Qubosonic energy. And to do that, we follow this procedure, which is different from the one I told you before. So first we solve the two-body state as or a single pair state as before. Then we build the creation operator for a single pair, and then we build the two co-boson bases, and at this point we reach the two pair or four particle part. And having that basis, we then calculate the overlap and Hamiltonian matrices, and with those matrices we find the ground state. And then having the ground state, we could calculate the fidelity between the true ground state and the one given by the ansatz. And we also calculate the conditional probability of finding a particle of a red particle in a given position when another red particle was found at zero position. To solve the two-body state, we rewrite the Hamiltonian in the center of mass and the relative coordinates. And when doing that, the Hamiltonian decouples, and the wave function is a product between the center of mass state and the relative state. And as we can see here, the solution of the center of mass equation are the free particle states. The relative states can also be obtained, and it turns out that when the interaction increases, so the system becomes more and more attractive, the relative ground states becomes more and more localized. That will be going from this black curve here to the blue one. And for a strong attractive interaction, we can approximate the relative state with this simple expression here. And in this plot, we can see the fidelity between the complete ground state and this approximation here, and it goes to 1 for strong attraction, meaning that this is this expression is a good approximation for the complete two-body states. We could also obtain the exact Schmidt decomposition of this two-body ground state, and with the Schmidt decomposition we were able to corroborate that this state fulfills all the criteria for good bosonic behavior proposed so far. Of course, the criteria that we, to the best of our knowledge, the criteria that have been proposed so far to the best of our knowledge. In this plot, we can see that the two particles are highly entangled in the when the attraction becomes more and more attractive, the linear entropy goes to its maximum value. And we also corroborate that the system fulfills some criteria for good bosonic behavior based on physical ideas, as this one here for each one of the Schmidt coefficients, these coefficients here, which comes from the notion that at low density prevents the overlap between the wave function of the fermionic parts, and therefore their fermionic character will not be important. Once we have the two-particle state, we build the creation operator for a pair like this one, where this operator here creates a red fermion at position X. And having the creation operator, we build the two co-boson bases here. And because of the symmetry of the problem, and since we are looking for the ground state, we can restrict us to the space with zero momentum, so that the ground state will have this form here, where this Km is a cutoff, while the Qubosonic state will have this other form like here, that will be all when all the coefficients in this expression are zero, except for the first one. And once we have the two co-boson bases, we need to calculate the overlap matrix, because the basis is not orthogonal. And in this step, we must use the commutation and anti-commutation relations for the creation operators, and then we must perform the resulting integrals. And the complete expression for the overlap matrix is this one. And the important thing here is that for a very strong attraction, we can expand this expression on this small parameter to obtain this other quite simple expression. And we can also compute the expression for the Hamiltonian, and we can also expand it on the same small parameter as before. And now we are left to find the ground state. So we need to solve this generalized eigenvalue system. And with the complete matrix elements, we can solve this numerically. And with the Taylor expansions, we can obtain some exact results. But before going to those results, we are ready to compute the Qubosonic estimation for the energy of the 4-particle ground state, which is this one here. And we can see that the Quboson ansatz is not giving us the correct 4-particle ground state, because the true energy will be obtained if we put here a 2, because n is the number of pairs, and we can see that this is a very large correction to the energy of 2 non-interacting pairs, and here we don't have such a very large correction. And even though the ansatz failed with the Taylor expansion of the Hamiltonian and also the overlap elements, we could reobtain the exact correction for the ground state energy, this one here, and we also could obtain the exact coefficients here. And then with those coefficients, we could calculate the exact fidelity between the quark state and the Qubosonic state, and we obtain this number here. This fidelity is not quite good, but it is in agreement with the previous results in the one-dimensional lattice model. So the results are consistent with the previous works in one dimension. And finally, we calculated the conditional probability here. We obtained this expression here, and it differs from the Qubosonic correlations. In this plot, we can see that the that the correct probability, which is this red one, is quite smooth. And the Qubosonic one, which is this gray one, is quite flat with an abrupt decay around 0. In 0, both probabilities must be 0 because the fermions of the different species cannot be at the same position. This flat probability is in agreement with the previous results in the lattice work. So the main conclusions are first, that the ansatz does not give a good approximation for the ground state because it doesn't capture the spatial correlation between the pairs. And second, that even though the ansatz fails, we could show how the Qubosonic theory, or using the complete formalism, we can recover the correct ground state. Then we see our work as a warning sign against the light use of the Qubosonic ansatz, especially in the description of one-dimensional problems. Beyond this particular case, and as a global conclusion, I will say that the Qubosonic formalism is a powerful toolbox to address few and also many body systems. It is also useful to address entanglement in many particle systems. And the ansatz or the Qubosonic formalism also allows to study a wide variety of systems. The particles can be fermionic or bosonic, distinguishable or indistinguishable. And the ansatz has evolved towards a framework merging atomic and molecular and quantum information and many body physics. And this is quite interesting, at least for me. And the main point I would like to stress in the context of this conference is that most of the proposed criteria for good bosonic behavior until now are related to entanglement. And even so, a proper criterion for good bosonic behavior is still elusive. The system, for example, fulfills all the entanglement criteria, as well as some other criteria based on physical ideas, and even so, the ansatz fails. So there is a fundamental underlying question, which is what is the role of entanglement when addressing composition? And this question is open. So thank you very much. And here are our emails and a photo of all the people that had been involved in the group. And also Martin is doing his PhD with Anna, and he will be presenting a poster on Friday about some related things. So you can see Martin's post.
Okay, thank you, Eloísa, for your talk. If there is a question or comment, you can indicate the chat, and we will give you the word. A question from Federico Paulie.
Hi, Eloísa. Thanks for this talk. I'm still trying to understand the physics of this. It's really complicated for me, because you mentioned that entanglement, I mean, in the situations in which the Qubosonic ansatz works, entanglement plays a key role. So when you have high entanglement, it works. But I wonder what happens in an atom. Suppose that you have an atom. But in an atom, if you have the right numbers of electrons and protons and neutrons, it will behave like a boson, right? But this atom could be in a thermical bath with no entanglement at all. So why an atom behaves like a boson? That I don't understand. I mean, I understand the idea, but it's so. Can you say something
actually
about that?
In the paper, In the paper of Tsutsiki, one of the PRL I show on the slides, they give us an example the hydrogen atom, and they said that we have two fermions, two distinguishable fermions, an electron and a proton, and they calculate the entanglement between the electron and the proton, and it is quite high. So that will be an explanation of why the hydrogen atom behaves as a boson.
But
I don't
how
know
can
if
it be
that
so high?
answer-
It's puzzling, you know, because I imagine an atom.
Because of the interaction.
Yeah. Oh, yeah. But also an atom is interacting with the electromagnetic fields, right? And it can be emitting or interacting with other atoms, like in a thermal bath. So it's really puzzling for me.
Yeah.
Does it mean that? Yeah.
Yes, you could think, for example, that when you have those other interactions, somehow those interactions interfere between, for example, the interaction between the electron and the proton, and then the atom like loses the bosonic behavior somehow.
Okay,
Yeah,
so you
I
say
would think something like that.